So today we're going to talk about study design and sample size. The noted statistician Sir Ronald A. Fisher once said, "Statistics is the study of populations, variation, and methods of data reduction." By this, he meant that a population implies variation, and a population cannot wholly be ascertained. So descriptions of population really depend on sampling. The samples that we collect need to be reduced in some way to summarize the information about the population. This is a problem of data reduction. Any statistical treatment must address the following four basic questions. What is the question? Can it be measured? Where, when, and how will you get the data? What do you think the data are telling you? The ordering of these questions reflects the process in science. For example, consider that we want to undertake a study to address the research question, does air pollution cause ill health? Note that our answers to questions 1 through 3 all focus on design. That is, question 1 is, does air pollution cause ill health? Question 2 may include remote sensing instruments designed to measure particulate matter and ozone levels. Question 3 may include decisions relating to locations of where to place remote sensing devices, how often they will collect data, that is, will they collect measurements weekly, daily, or continuously, such that the data would be streaming? How will data from these devices be downloaded or transferred to the analyst? It isn't until the last question that we focus our attention on the analysis of the resulting data. Note that when addressing what the data are telling you, you need to be aware that there is a difference between statistical significance and clinical significance. There are several rules of thumb that we should consider when making decisions about the study design. First, observation is selection. It is very important to recognize the selection process when collecting data. For example, during World War II, some airplanes returning from bombing missions, while others did not return. Planes that returned often had bullet holes in various locations on the aircraft. When trying to identify what areas on an airplane should be reinforced before sending them back out, most people suggested that those areas of the plane that were most commonly bulleted should be reinforced. It was a statistician, though, that suggested reinforcing areas where there weren't bullet holes. That is, planes not returning from their mission likely had been hit in more critical areas, and those areas were the ones that needed reinforcement. He was actually right. The take-home message here is, know your sample. We need to make sure that observations are representative of the population we are interested in. In this case, the planes that did not return from their bombing missions were of primary interest. Replicate to characterize variability. We need to characterize the variability that we observe. Variation may be systematic, that is, it is predictable, or non-systematic, that is, it is random. Randomization of observational units is one method that is commonly used to ensure replication. Variability occurs at multiple levels. For example, in an educational setting, variability occurs student to student, classroom to classroom, school to school, and district to district. It is important to recognize that there are different levels that all contribute to variation. Invalid selection is the primary threat to valid inference. Selection bias occurs when the sample is not representative of the population of interest. It is therefore very important to be able to describe the selection process. Compared with experimental studies, observational studies provide less robust information. There's no explicit random mechanism in observational studies. We often make the assumption of independence in observational studies, which may or may not be true. For that reason, it is important to distinguish between randomized and observational studies. Often convenience sampling is used in observational studies. In that case, precision of our statistical summaries is less of an issue than is bias. Look for a physical model underlying the data being analyzed. Assume a statistical model, such as a linear model, is a first good start. It is crucial to have a broad understanding of the subject matter involved. Statistical analysis is much more than carrying out routine computations. Some other rules of thumb in statistics is keep models as simple as possible, but not more simple. The famous rule called Occam's razor provides guidance for model selection. Everything else being equal, the simpler model among a collection of models is to be preferred. In statistics, we often call this parsimony, or we're looking for a parsimonious model. Understand the components and the purpose of an omnibus quantity. Examples of omnibus quantities are p-values, f-tests, effect sizes. They're reduced using multiple model reductions and parameters. For the same value of an omnibus quantity, many component values are possible. A 2x2 contingency table can be summarized using odds ratios, kappa statistic, a chi-square statistic, Youdin's Q, etc. Two summaries are also sensitivity and specificity, positive predictive value, negative predicted value, proportions in columns and row margins. Selection of these quantities depend on the study's purpose. Omnibus quantities fill a purpose of summarizing, but are less useful for understanding basic mechanisms. Do not multiply probabilities beyond necessity. Remember, probabilities are bounded by 1, so that multiplying enough probabilities will always yield a small number. It's a very interesting example that occurred in history. In 1964, there was a purse snatching in Los Angeles, California, where, quote, a blonde woman with a ponytail snatched a purse from another woman, end quote. The thief fled on foot, but was later spotted entering a yellow car and driven by a black man with a beard and a mustache. A woman was finally located who matched this description. The prosecuting attorney assigned probabilities to the above facts. A probability of 1/3 was assigned to a woman having blonde hair, of 1/10 for having a ponytail, 1/10 for having a yellow car. A black man with a beard was assigned a probability of 1/10. A black man with a mustache was assigned a probability of 1/4. An interracial couple in a car together in 1964 was assigned the probability of 1 out of 1,000. These probabilities were then multiplied together to produce a probability of 1 out of 12 million. This probability was calculated under the null hypothesis of no association and was judged to be so low that the court convicted the couple that was identified. Problematically, the probability could have been made even smaller by creatively adding additional characteristics. Note also that multiplication of these probabilities assume that the events are all independent. Interestingly, the conviction was later appealed by the California Supreme Court and it was overturned. Again, if small probabilities are associated with unlikely events, then by suitable selection, the joint occurrence of these events can be made arbitrarily small. Another rule of thumb is to use two-sided p-values. The concept of equipoise in hypothesis testing usually implies that both sides of the null hypothesis are equally plausible. If the null hypothesis is false, it is not known a priori which direction the relationship will go. Note that although an F-test uses the F distribution as its reference distribution and so is one-sided technically, in reality, the null hypothesis associated with the F-test is actually two-sided. If a researcher argues for a one-sided test as a matter of principle, it is recommended to set the type 1 error rate at 0.025 rather than 0.025. I'm sorry, rather than 0.05. When designing experiments or observational studies, focus on p-values to calculate the sample size. When reporting results, focus on confidence intervals. Hypothesis testing and estimation are two sides of the same coin. Hypothesis testing is somewhat more formal in that the alternative hypothesis must be defined if a sample size calculation is to be carried out. Use at least 12 observations in constructing a confidence interval. The basic elements determining a confidence interval are sample size, an estimate of variability, and a pivotal variable associated with the estimate of variability. The width of a confidence interval involving estimation of variability and sample size decreases rapidly until 12 observations are reached, and then decreases less rapidly. The reciprocal of the square root provides a nonlinear drop-off. Related to this, for sample size greater than or equal to 20, a point estimate plus or minus 2 standard errors has approximately 95% coverage for a wide variety of distributions. Let's look at an example of 12 observations are needed for confidence interval construction. Taking our sample size to range from 2 to 20 observations, our value from a t-distribution can be obtained in R using the QT function, noting that we want a two-sided confidence interval at a level of 95%, and noting that we have n-1 degrees of freedom, we would get these t values. Now, if we plot with n on the x-axis and our t value on the y-axis, I'm going to connect these points using a line. You'll notice that in our graphic, that as we get a larger sample, in fact, right about where we hit 12, our t-value levels off. So that's why we need 12 observations for calculating confidence intervals. Another rule of thumb is always know what unit of variable is stored in. Remember, gallons are different from liters, metric are different from non-metric scales, Celsius is different than Fahrenheit. Do not let the scale of measurement rigidity determine the method of analysis. The scale of measurement can be binary, ordinal, count, or continuous, but that is less important than the distribution of the values on the scale. Also note, the prominent schools of statistical inference include Neiman-Pearson, likelihood, and Bayesian methods. The practical applied statistician uses methods developed by all three schools as appropriate. So let's consider the means of two independent samples. Suppose their values are 10 and 22, and that they have equal standard errors of 4. The 95% confidence interval for these two statistics can be calculated by hand or using R. What, if anything, can we conclude about these two means if calculating their respective 95% confidence intervals? What if we calculate this Z statistic and the confidence interval for the difference between those two means? Again, we said that we want to suppose two means are 10 and 22. So if we wanted to calculate the lower limit for group 1, I'm going to call this L1, representing the lower limit of group 1. Its value for the mean is 10, and we're going to use the standard 95% confidence limit so that our Z statistic is 1.96. We said before that both of our means have a standard error of 4. The upper limit given by U1 is 10 plus 1.96 times 4. We said group 2 had a mean of 22. So the lower limit for group 2 is 22 minus 1.96 times 4, whereas the upper limit for group 2 is 22 plus 1.96 times 4. Now, if we put together the lower limit of group 1 and its upper limit, we see that the confidence interval ranges from 2.16 to 17.84. For group 2, the confidence limit ranges from 14.16 to 29.84. Even though these confidence intervals overlap, that does not indicate non-significance. Instead, we need to calculate the Z statistic comparing these two means. So the Z statistic would be given by the difference in the two means divided by the square root of their pooled standard errors. So we get a Z statistic of 2.12 roughly. The two-sided p-value can be calculated using our p-norm function. And that p-value would be 0.0339. Notice that we would reject the null hypothesis and conclude that these two means are indeed significantly different. Alternatively, we could calculate the 95% confidence interval for the difference. For the lower limit of the difference, we have our difference estimate minus 1.96 times the square root of the pooled standard error. The upper limit is going to be that same quantity, except we're adding these terms. Notice that our confidence interval for the difference does not include the value of 0, so our conclusion is the same. A frequently asked question in clinical research is, how many subjects do I need? So often as statisticians, you are called upon to estimate the sample size for a study or a clinical trial. Let's watch this YouTube link. All right, so that's somewhat of a silly example, but I have to say that I have encountered investigators that are very much like that. So note that when estimating the needed sample size, it is important to know the measurement scale of the primary outcome. That is the outcome continuous, discrete, or something else? Perhaps it's survival or binary. For continuous measurement, the Gaussian distribution is the default distribution for sample size estimation. For a binary or dichotomous outcome, the binomial distribution is the default distribution. There are multiple ingredients needed for sample size calculations. The first three are required for any sample size estimation problem. They are alpha, the type 1 error, which is the probability of rejecting the null hypothesis when in fact it is true. The type 2 error, or beta, which is the probability of not rejecting the null hypothesis when in fact it is false. Power, which is 1 minus beta, represents the power of rejecting the null hypothesis when it is false. And for a continuous measurement, we additionally need these items. The variances under the null and the alternative hypotheses, note that these could be the same. The means under the null and alternative hypotheses. And when we use these quantities together, we can estimate the sample size into groups for our study. So sometimes it's challenging to select an appropriate alternative hypothesis. This should be done in conjunction with the subject matter experts, who should be able to verbalize what sort of difference would be clinically significant. Typically, though, it is very straightforward to specify the null hypothesis, as the null hypothesis is assumed to be the hypothesis of no effect. One area of clinical research where this is not true is in equivalence testing, such as in designs of clinical studies which seek to determine whether a generic drug is equivalent to the originally formulated name brand drug. Sometimes preliminary estimates are needed for sample size calculations and they're not available. That is, we may not have data that suggest what values of the variances and means to use. In fact, if we really had good estimates, that may indicate that the study has already been done, so that there's no need to do this new study. In some cases, we may have some or partial pilot data that could be used, or we may be able to appeal to the published literature for obtaining plausible values. Other times, it does take some guesswork so that the statistician is required to ask probing questions of the subject matter experts. Though certainly not used for every study, it is fairly standard to use an alpha of 0.05 and beta of 0.2. I will say, for gene expression and other high throughput genomic studies, alpha is usually set to a very small value, such as 0.001, to account for the fact that multiple hypothesis tests will be performed. Beta may be set to a larger value if you want to mitigate the chance of missing important results. Regardless, the critical value defines the boundary between the rejection region and the non-rejection region. In this figure, the distribution on the left represents the distribution under the condition of the null hypothesis, which you can see is centered here at 0. The distribution to the right represents the alternative and is shifted to the right by delta. So delta is our alternative difference. We will reject the null hypothesis if our test statistic lies in either tail of the leftmost distribution. As can be seen, the probability of making an error is defined by beta, which is the probability of this left tail region of the rightmost distribution. The critical value, defined by the boundary between the rejection region and the non-rejection region. This value must be the same under both the null and alternative hypotheses, so that leads us to this fundamental equation. Substituting in mu sub 0 minus mu sub 1 for delta and solving for n, yields the following formula for the sample size required for comparing two population means with a common variance sigma squared and equal sample sizes for the two groups. Using the traditional alpha equals 0.05 and beta equals 0.2 values, and using the Gaussian distribution as our reference distribution, yields a z of 1.96 and also a z for power of 0.84. We can estimate the required sample size using this formula that's provided. Note that in a pinch, such as during a meeting, this formula can be approximated by this equation. Note that the delta, which is in the denominator and is squared, is simply the denominator of our sample size formula. Therefore, delta can be considered as a standardized difference, which can be helpful for the researcher who does not know the variability associated with their data. So we're going to use R to do some sample size calculations. Going back to the formula on slide 11, and noting that our alpha level, we've specified to be 0.05, our beta is 0.2, which corresponds, to a power of 0.8. That means we can get our associated reference values from our normal distribution. We can use our Q-norm function. Remember that we're doing a two-sided test, so we have to divide alpha by 2. So we see our z associated with alpha is roughly 1.95, and the z associated with beta is roughly 0.84. Now notice, if we calculate the numerator of our sample size formula that appears in slide 11, we get roughly 16. That is why the approximation has 16 in the numerator. Now, let's take a specific example. Let's suppose that mu naught is 6 and mu1 is 8. And we have a common variance of sigma squared equals 16. So what we want to do is estimate the sample size that's needed to detect a difference in these means using an alpha of 0.05 and a power of 80%. So we said that our mean under our null hypothesis is 6. The mean under the alternative hypothesis is, of course, 8. We've already specified alpha to be 0.05, and we've already specified beta to be 0.2. We have to also specify our standard error, which is the square root of our variance term. So the sample size formula, borrowing from what appears on page 11 of your slides, would look like this. In the denominator, we have the difference in the two means divided by the standard error and we get a sample size of 62.79. Now, anytime you come up with a sample size calculation, if it is not an integer, you round up. So we would actually say that we need a sample size of 63. Note that when using the approximation formula, our delta is going to be that denominator term that's inside the squared component. So this is our delta term, and our sample size approximation, which I'm going to call n dot approx, is 16 divided by delta squared. And that's 64. So it's a difference of one patient. We have 63 here and 64 using our approximation formula. Now there is a function that's in the stats package. This is one of the base packages in R, and it's called power.ttest. If you look at the help on power.ttest, it will compute the power for a 1 or 2 sample t-test. You can specify the sample size. In that case, it will calculate the power, or you can specify the power, and in that case, it will give you the sample size. Okay, so notice that if we want the sample size estimated, we leave that blank. Delta is actually the difference between your two sample means, the mean under the null hypothesis minus the mean under the alternative. The SD is our sigma. Our significance level is our alpha term. It does default to 0.05. The power is actually set to a null value, so we would have to specify that if we want to calculate the sample size instead of find the power. By default, it does use a 2-sample test. You can change that. Also, the alternative is a 2-sided test. Okay, so this is for a 2-sample, 2-sided test by default. If you had a 1-sample test, you could do that as well. Again, the recommendation is to always use a 2-sided test in terms of an alternative. All right, so let's look at it for this particular example. We're going to say power.t.test. Our delta value is our mu naught minus our mu 1. Our SD is stored in our sigma variable. If we want to specify that the sig level is 0.05, we can, just to make sure we know everything that we've specified is accurate. Our power is 0.8. I'm going to go ahead and specify everything so you can see all of the details. So this is a 2-sample test. And let me go to the next line so that you can see what I'm typing. Our alternative is also a 2-sided test. Okay, when I hit enter, I do get that our required sample size is 63. Now, there is a package in R that has more flexibility in it and is sometimes preferred, especially for grant application. And this is called the PWR, which stands for power. So go ahead and install that if you haven't installed it on your R installation. And I'm going to go ahead and attach that library here. Now, the corresponding function in the PWR package is pwr.t.test. It stands for power.t.test. The syntax is very similar. We have the N, which we can specify or leave it blank if we're solving for the power. D is the delta. Okay, so that is not the difference in the means, but it is our delta value. The sig level, again, defaults to an alpha of 0.05. The power is left blank in case you want to supply the sample size and solve for power. Here we want the power to be 0.8. And it does default to a 2-sample t-test, and the alternative is by default 2-sided. So let's go ahead and we're going to use this. And I'm going to store the results of this into an object, and I'll show you why in just a minute. So again, the function is pwr.t.test. Our D is equal to our delta value. Our sig.level will specify again to be 0.05 just for completion. And the power again is 80%. And our alternative is indeed 2-sided. Okay, the defaults would be used for anything else. Now, our results went into our object called PWR, and you can see that the sample size is the same. So why use this? The reason is that we can plot the result, and it's the plot that makes this package and the resulting object much more flexibly used. So I can say sample size in each group. Remember, the n that we're solving for is the sample size in each group. So we need 64 subjects in each of the two groups. All right. So hopefully you can see that we have the sample size along the x-axis and we have the power along the y-axis. There is a line that's drawn where we achieve 80% power, and this would be at the point where we have 64 subjects. So you can see, well, if an investigator can be given this plot, and they can look at this plot and see whether or not they want to increase the power, how many more subjects that would be. Maybe they don't have a lot of resources and they want to see how low they can go. So unfortunately, when working with investigators, they often don't have preliminary data. When you don't have an estimate of the variance or the standard deviation, sometimes you might have a few observations that were collected, and the range of those observations can be used to provide bounds for the standard deviation. Given that the range is the maximum value of your observations minus the minimum value of your observations, the bound on the standard deviation is given by these two endpoints. Therefore, an alternative estimate for your standard deviation can be provided by the range. So let's suppose that we have some data in R. Let's just put in some values. So we'll put in a value of 44, 48, 52, 60, 61, 63, 66, and 69. So there's a function called range in Stata, and it gives you the minimum and the maximum value. So we could calculate our range which we get our range of 45. Note that the length of our data vector is our current sample size. So our lower limit would be the range divided by the square root of 2 times the quantity n minus 1. Whereas the upper limit would be n divided by n minus 1 times the range divided by 2. So if we look at this, our range on our, the limits on our range would go from 6.68 to 14.2. So we would suspect that our standard deviation would fall somewhere in here. We could take a midpoint. If you want to be very safe, you can take one of the extreme values, depending upon how many resources you actually might have. In some cases, the data may have already been collected, as in a secondary analysis of an existing data set. So the sample size is already fixed. In that case, one often states what the detectable difference can be expected to be. The detectable difference of a given sample size can be estimated using this formula. If the variances and the sample sizes are not equal, the values associated with the null and alternative hypotheses can be inserted into our usual equation, and then we can solve for delta. Recall that sometimes the means are unknown, but the researcher may have an idea of relative treatment effects and variability. For example, you may ask, what kind of treatment effect are you looking for? They may respond, oh, I'm looking for a 20% change. Then of course you ask the follow-up question, so how much variability is there in your observations? And they'll respond something like, oh, about 30%. In such a case, you can use the percent change in means because that's linked to the ratio of the means. In that case, the sample size formula is given by this equation here. All right, so in the example I just described, we have essentially a coefficient of variation of 0.30. That's how much the researchers said that they would expect the observations to vary, by about 30%. The percent change, they said they're interested in, I think, a percent change of 20%. So our baseline is actually 100. And so we take 1 minus that expected percent change. So then our sample size is given by 16 times the CV quantity squared divided by the log of that PC quantity squared. So we get 28.92. So in other words, we would want 29 observations in this particular case. So we've looked at some examples of calculating the sample size for a continuous outcome. For a binary outcome, the null hypothesis is that the proportion with the condition in the two groups are equal, or in other words, that their difference is 0. And the alternative is that the two proportions are not equal. This is a sample size formula assuming equal size groups. It's given by this equation. So for a binary outcome, we have the problem for pi under the null hypothesis being equal to 0.3 and pi under the alternative hypothesis being equal to 0.1. What is the required sample size to detect that these are different? Using an alpha of 0.05 and a beta of 0.2, which means we have 80% power. So we already have stored in our R session, if you've been following along, the associated values for alpha as well as for beta. So we don't have a need to further calculate those. Now we do have to put in our pi naught value of 0.3 and our alternative value of 0.1. Okay, so the average value would be achieved by adding those together and then dividing by 2. Whoops. All right. So then the sample size using the formula on our slides is going to be given by Z alpha times the square root of 2 times pi. That's pi as in what we just stored, the value of 0.2 times 1 minus pi. And then we have plus, and I'm going to erase this and go to the next line so that you can see what I'm typing. Z beta times the square root of pi naught times 1 minus pi naught plus pi 1 times the quantity 1 minus pi 1. And that entire expression is squared. And then we're going to divide that entire expression by pi naught minus pi 1 and that quantity squared. All right. So if you've done the typing correctly, you should get that the required sample size per group is 61.6 roughly. And so that means we want 62 observations collected. Now, there is a function called power proportion test. Okay, it's like power for a proportion test. This is in the statistics or the stats package. And looking at the help on it, we're wanting to calculate the sample size. We specify the null condition, the alternative condition, the significance level. We're going to specify our power. It is an alternative two-sided test by default. All right, so I'm going to store this. Oops. I'm going to call it power proportion, essentially. And I'm going to use this function, power.prop.test, where our pi 1 is 0.3, our pi 2 is 0.1, our significance level is 0.05, our power is 0.8, and our alternative is two-sided. All right. So then when I type the result of my object, I get the same thing. There's a little bit of, yeah, I guess it's rounded to be the exact same expression here. Now in the power, the PWR package, the corresponding method is called PWR2P.test. Okay. So this is the function in the PWR package for calculating the sample size or the power for two proportions. Note that it's required for the user to pass this term called H. H is actually the effect size rather than the difference between the null and alternative proportions. Now, there is a function for calculating the effect size, which I'll show you in a minute, but we want to pass to it the effect size, probably leave n blank because we already have our power specified as 0.8. And we can leave alternative to the default of two-sided, or we can put that in. All right, to calculate the effect size, there is a function called es.h, and you pass to it the null and alternative proportion. All right. So what we're going to do is we're going to just do this all together, and I'm going to call this power prop 2. Okay, so the first one is using the basic stats package. This one is going to be using our PWR function. So it is PWR.2P.test, and we're going to pass to H the value that results from our effect size estimate of pi naught and pi 1. Okay. Our significance level, again, we could leave this at the default, or we could specify it so that we type everything out and know exactly what we've put in. All right. All right. So we can look at the result, and we see that the sample size is a little bit different than what we calculated before. That's because it does some kind of an arcsign transformation when it's calculating the sample size. It's completely fine. So don't use this because it comes out with a slightly lower sample size calculation. You would still want 60 subjects rather than 62 per group. Regardless, it's about the same. The nice thing again about this function is the plotting ability, because sometimes people really want these in their grant applications. So we can plot our resulting object. We can give the x-axis a nice label. And you get this nice plot so that you can kind of see allowable ranges for your sample size, and you don't have to keep refitting the function, but you can see exactly where your sample size would go if you wanted, say, 90% power, or if you wanted 50% power. I don't know why you would want 50% power, but you can see what kinds of options you have there. So far, we've talked about developing sample size plans when you're enrolling the same number of observations or subjects per group. Suppose that n observations are required per group, but in fact, you're only going to have n naught available for one group, and that value is somewhat less than n. This can happen in a number of scenarios, such as when there just simply aren't enough subjects that experience a certain condition that you're studying. So we can still get equal precision with n naught observations in group 1 by using the approximate rule that k equals n, the sample size. Okay, and so essentially we want to use this rule, which is based on these equations. Okay, so let's see how this would work in practice. Let's suppose that we're supposed to have 64 subjects per group, but in fact, in one of the groups, we can only, at maximum, enroll 50 subjects. So we can calculate K using our formula. Oops, I need it divided by sign. Okay. So we have this value K. Now when we multiply K times n naught, whoops, we get 88.89. What does that mean? That means we know we can enroll 50 subjects in our first group. To get equal precision, we have to enroll 89 subjects into our second group. Now there is a function that does something like this. It's in the PWR package. It's called PWR-diff.n. Okay, whoops, and it, oh, sorry, that's not the right name of the function. It's called PWR-T2N.test. Okay, so this function in the PWR package is for calculating the sample size when the group samples are unequal. All right, so we can specify N1 as 50, leave N2 blank, it will solve it for us. We do have to specify D delta, which is our effect size, the significance level, power, and alternative. We can let the alternative default to two-sided, or we can just force that in. So I wanted to actually name my object power.diff.n. All right, and we're going to use our PWR-T2N.test function. We're going to specify what sample size we can collect in our first group. We can let the second group size be null because we want to calculate that. Let's just use the delta that we had from before. And the sig level, of course, we're going to use the standard 0.05 level with a power of 80% and an alternative that is two-sided. And looking at this, we get basically the same thing. 88 subjects would need to be enrolled in the second group to achieve the same level of precision when we don't have equal sample sizes in the two groups. So sample size calculations for a survival or time to event outcome are more complex. Suppose we're designing a clinical trial to include two groups, a new treatment that's experimental and a standard treatment, or our control treatment, are going to be compared. We need to specify what log hazard ratio of beta we want to detect. This is what we're wanting to test. Now, the total number of events is what we need to specify, not the total number of subjects that we enroll. Remember, not every subject that we enroll will experience the event of interest. So the total number of events is given by this equation, where here, P is the proportion of study subjects in the experimental group, Q is 1 minus P, or the number in the control group, proportion in the control group. Alpha, again, is our type 1 error. This C sub alpha is the upper quantile of our critical value of the test. And then we also have Z associated with our power. So what can be difficult in the survival outcome is to determine what kind of beta or what size of beta you should use. Under proportional hazards, beta would be equal to this expression. So suppose you wish to compare an experimental to a standard treatment, and that 5-year survival under the standard treatment is approximately 30%, and that we anticipate that experimental treatment will increase survival to 45%. So we can calculate our beta using this quantity. So alternatively, we can assume exponential distributions, which is going to be based on the ratio of medians. So let's suppose that the standard treatment has a median survival of 1 year, and we want to detect a 50% increase, which means that then someone would survive to 1.5 years. Then looking at the ratio of those medians would give this value. So let's assume we have a study that we're trying to decide, and we want a two-sided test with alpha of 0.05. We want 90% power to detect the anticipated hazard ratio of 0.663. Again, either under proportional hazards assumption or assuming exponential model, we have similar estimates for the anticipated hazard ratio. So we have in this case, C sub alpha of 1.96 and Z of power of 1.28, again, because we're using a power of 90%. And the study is going to allocate patients equally to the two treatment groups. So P equals Q, since Q is essentially 1 minus P. So plugging those numbers in, then we require 249 deaths. We have to then back calculate how many observations we expect to enroll in our study to observe 249 deaths. So calculating sample size for survival endpoints is much more challenging because we have to decide how many subjects to enroll in the study in order to obtain the required number of events. In our example on the previous slide, we needed 249 subjects to be enrolled and experience the event, which means we need a lot more subjects enrolled in the study than just the 249. 4 factors are important for this second calculation. We need to consider the length of the accrual period, that is the length of the enrollment and recruitment period, the enrollment rate, the additional follow-up time between the last enrollment and study closure, and also the survival curve for the control group. So some concluding remarks about the sample size lecture material. First, sample size calculations should be based on the way the data will be analyzed. It's always very challenging to read grant applications or clinical trial designs and see that the sample size calculation is based on a formula that is not the kind of formula that will be used in a planned statistical analysis. Also, carrying out some other statistical procedure during the analysis may alter the anticipated power.